Hello, I am Ehsan Jafari, an expert in membrane technology. Before we start learning this lecture, just a quick note. I am available for your private consulting, system design, troubleshooting, and procurement. If you need professional support for your business, just hit me up on WhatsApp. Now let's begin the tutorial.
Section 4. Membrane Design and Evaluation. At first, as always, let's have a look at the content. This section is presented in 4 lectures. In this lecture, we have general concepts before the design, including stage and array in reverse osmosis and nanofiltration, pressure drop and its effect on membranes, osmotic pressure and reverse osmosis, mass transfer, separation mechanism, and mechanisms of solute rejection in reverse osmosis and nanofiltration. In the next lecture, we have designed a reverse osmosis system in 10 steps. In lecture 13, evaluation of reverse osmosis systems such as permeate flow rate, water flux and permeability, solute rejection and cell passage evaluation and recovery will be presented. At the end of this lecture, energy and sustainability consideration for microfiltration, ultrafiltration, nanofiltration and reverse osmosis, as well as residuals disposal will be presented. Now we start with general concepts before the design. Reverse osmosis and nanofiltration systems, stage and array. There are different types of flow configurations in reverse osmosis systems, including single stage, two stage, single pass, and two pass systems. The membrane elements are enclosed in pressure vessels. Reverse osmosis systems can contain one to several groups of pressure vessels. Each group of pressure vessels is called a stage. The concentrate from one stage can be fed to a subsequent stage to increase water recovery. In this figure, you can see a three-stage system. Reverse osmosis systems can also have distinct reverse osmosis units referred to as a pass. The permeate from one stage can be fed to a second stage to increase solute removal in a two-pass system. For applications where high purity water is required, two-pass systems are common because they essentially treat the water twice in two distinct systems. These flow configurations can be optimized, influencing overall system performance. A unit of production capacity which may contain one or more stages is called an array. In this figure, you can see a three-stage array as well as two-pass system. Pressure drop and its effect on membranes. Pressure drop is defined as the loss of pressure between the inlet and outlet of a membrane system housing, that is a pressure vessel or element. When a pressure drop exceeds the normally reported value, it indicates that physical plugging or scaling of the membrane is taking place. An excessive pressure drop can cause the membrane and or materials of construction to move and sometimes break, eventually resulting in a complete failure of the membrane. Pressure vessel systems typically operate at transmembrane pressure, a pressure drop between the feed and permeate between about 0.4 and 1 bar. Pressure vessels can be configured with either outside in or inside out membranes. In spiral-wound modules, designs minimize the pressure drop encountered by the permeate flow traveling towards the central pipe. If a single membrane envelope were used in a large membrane area module, the path taken by the permeate to reach the central collection pipe would be several meters long, depending on the module diameter. Such a long permeate path would result in a large pressure drop in the permeate collection channel. By using multiple short envelopes, the pressure drop in any one envelope is kept at a manageable level. The second type of hollow fiber module is the bore side or inside out. The fibers in this type of unit are open at both ends, and the feed fluid is circulated through the bore of the fibers. To minimize pressure drop inside the fibers, the diameters are usually larger than those of the fine fibers used in the shell side or outside in feed system and are generally made by solution spinning. Osmotic pressure and reverse osmosis. The pressure required to balance the difference in concentration of a solute is called the osmotic pressure. An understanding of osmosis pressure is essential to an understanding of reverse osmosis. Osmosis is the flow of solvent through a semi-permeable membrane from a dilute solution into a concentrated one. Osmosis reduces the flux through a reverse osmosis membrane by inducing a driving force for flow in the opposite direction. To get the concepts of diffusion and osmosis, look at these figures. Consider a vessel with a removable partition that is filled with two solutions to exactly the same level as shown in figure A. The left side is filled with a concentrated salt solution, the right with pure water, and the partition is gently removed without disturbing the solutions. Initially, the contents are in a non-equilibrium state and the salt will eventually diffuse through the water until the concentration is the same throughout the vessel. On figure B, the top of the vessel has been closed and fitted with manometer tubes and the removable partition has been replaced with a semi-permeable membrane. The semi-permeable membrane allows the flow of water but prevents the flow of salt. Filling the chambers with salt solution and pure water again creates a thermodynamically unstable system which must be equilibrated by diffusion. Because the membrane prevents the flux of salt, however, mass accumulates in the left chamber, causing the water level in the left manometer to rise and in the right manometer to drop. This flow of water from the pure side to the salt solution is osmosis. Two opposing forces contribute to the rate of water flow through the semipermeable membrane. First, the concentration gradient, and second, the pressure gradient. These opposing forces are exploited in reverse osmosis. As shown in figure C, applying a force in excess of the osmotic pressure places the system in non-equilibrium with a pressure gradient exceeding the concentration gradient. Water would flow from left to right, that is, from the concentrated solution to the dilute solution. The process of causing water to flow from a concentrated solution to a dilute solution across a semipermeable membrane by the application of an external pressure in excess of the osmotic pressure is called reverse osmosis. In a dilute solution, osmotic pressure can be approximated by the Van't Hoff equation. This equation was derived assuming infinitely dilution solutions, which is often not the case in reverse osmosis. To account for the assumption of diluteness, the non-ideal behavior of concentrated solutions, and the compressibility of liquid at high pressure, a non-ideality coefficient must be incorporated into equation. To better understanding, I have given an example. In this example, calculate the osmotic pressure of 1000 mg per liter solution of sodium chloride at a temperature of 20 degrees Celsius, assuming an osmotic coefficient of 0.95. To solve this problem, the osmotic pressure of sodium chloride has to be determined by calculating the molar concentration of ions. Sodium chloride dissociates into two ions, sodium and chloride, so the molar ion concentration is double the molar concentration of added salt, and then using modified Van't Hoff equation, osmotic pressure can be calculated. It has to be noticed that the number of temperature has to be converted to Kelvin. Mass transfer of water and solute through reverse osmosis membranes. The active layer of a reverse osmosis membrane must selectively allow water to pass through the material while rejecting dissolved solutes that may be similar in size to water molecules. Separation cannot occur if water flows through pores in the membrane and small ions are carried convectively with the water. Thus, physical sieving is not a primary separation mechanism. The physicochemical processes that control separation in reverse osmosis are rooted in the principles of mass transfer. Separation mechanism and solution diffusion model in a dense material. A number of models have been developed to describe mass transfer through reverse osmosis membranes. The most common model envisions a reverse osmosis membrane as a dense material, meaning a material that is non-porous or there are no holes in it, that is nonetheless permeable. Water and solutes dissolve into the solid membrane material and diffuse through the solid. Diffusion occurs by movement of the water and solute molecules in the direction of the pressure and concentration gradients, such as Gibbs energy. Diffusion of water and solutes into a solid material occurs if the solid is loose enough to allow individual water and solute molecules to travel along the interstices between polymer molecules of the membrane. When a concentration gradient is present between two phases in contact with each other or between two locations within a single phase, matter will flow from the region of higher concentration to the region of lower concentration at a rate that is proportional to the difference between the two concentrations. In other words, the driving force for solute flux is the difference in concentration, and the flux of solute through reverse osmosis membrane is expressed by the following equation. Flux through the membrane is determined by both solubility and diffusivity. Flux is the product of a mass transfer coefficient and a driving force, usually a concentration gradient. The magnitude of the driving force depends on the solubility of the material in the solid phase. Separation occurs when the flux of the water is different from the flux of the solutes. Since the physicochemical phenomena that control separation are dissolution and diffusion in the solid phase, this model is known as the solution diffusion model. The solution diffusion model predicts that separation occurs because the solubility, diffusivity, or both of the solutes are much lower than those of water, resulting in a lower solute concentration in the permeate than in the feed. The basic mechanisms of rejection are differences in the solubility and diffusivity in the membrane, of course along with electrostatic repulsion at the membrane surface. Solubility and diffusivity are affected by polarity, charge, and size. Reverse osmosis membranes are often negatively charged in the operation. Negatively charged ions may be rejected at the membrane surface due to the electrostatic repulsion, and positively charged ions may be rejected to maintain electroneutrality in the feed and permeate solution. Large molecules would be expected to be less soluble in the membrane material and also have lower diffusivity through it. Dissolved gases such as hydrogen sulfide and carbon dioxide, which are small, uncharged, and polar, also permeate reverse osmosis membranes well. Monovalent ions such as sodium and chloride permeate better than divalent ions such as calcium and magnesium because the divalent ions have greater electrostatic repulsion. Boron present in water as boric acid and silica present in water as silicic acid are weak acids that have poor rejection in their neutral forms. High rejection can be achieved by raising the pH. Acids and bases such as hydrogen chloride or sodium hydroxide permeate better than their salts such as sodium or chloride because of decreased electrostatic repulsion. Reverse osmosis membranes are capable of rejecting up to 99% of monovalent ions. But nanofiltration membranes reject between 80 and 99% of divalent ions with a considerably poorer rejection of monovalent ions. Now this lecture finished. Let me know your solutions for the homework problem. You can also download it from the website. In the next lecture, we will start the reverse osmosis system design in 10 steps. Thank you for your attention.